I forgot to show you the derivation of the energy, and we derived that the main equation was that velocity was plus minus omega, the highest displacement minus the displacements. So an object that is in a simple harmonic motion has also a velocity. So it has a mass, a constant mass, and a velocity. So it has a kinetic energy. So in this video we will talk about the equations of energies, but in terms of simple harmonic motions. So we know Ke is half mv square, and the velocity equation we found in the previous video, the previous class, is that it's plus minus omega root over x naught minus x square. So we have a square here. So if we work that out, what we get is omega square, and the root is cancelled. So we are left with this. And we see that the plus minus is no more in the equation because of the square. So we are only left with plus, but you don't have to write it here. And that is the equation for kinetic energy that is in a simple harmonic motion. Now a spring can also be in an oscillation and have a simple harmonic motion, and this point can go back and forth, and we see it's returning to the same point. So thus it's having a simple harmonic motion. So we know that the energy it has is the potential energy, which we can write as U. So that's half kx square. Now we know from Hooke's law that that force is actually proportional to the force we provide here in a spring is proportional, or the distance actually, that is the extension is actually proportional to the force. So we got an equation that we obtained a equation which is minus kx. So and the k is actually the spring's constant. And and from the Newton's law, we have the total energy is mass into acceleration. So as we see that force is this, so if we substitute it, it becomes minus kx equals to ma, and in terms of acceleration we get minus kx divided by m. Now from the simple harmonic motion chapter, we also got that acceleration is also minus omega x square x. So we can actually equate those. A equals to a. So that's minus omega square x equals to minus kx divided by m. So we can cancel out the minuses and the x's. So what we are left out is omega square is equals to k divided by m. So the k or the spring constant comes out to be omega square m. So our goal was to bring somehow to bring omega here, because if you look at the previous equation, like for instance the velocity, we have omega, and for the acceleration we have minus omega x square. So omega is a must to have in simple harmonic relationships. So therefore we just so derived an equation that has to have, have omega in it. So that's half, and we get k. So we just substitute. So k is omega square m. This is the k, and finally x square. So we got two equation. Firstly for the kinetic energy, and then for the potential energy for simple harmonic motion. And one thing that you have to know is that something super important is that like, in SHM we consider there is no energy loss. There is no dissipation of forces, and everything is like perfect. So the total energy, if and also the conservation of so we get a total energy for SHM which is so all the energies are between kinetic energy or the potential energy, so nothing is lost. So it's the kinetic energy plus the potential energy EU, and it's easy. Like if you are if you just substitute that E for kinetic energy, we have half m. It's half m omega square x naught square minus x square. So this is for the kinetic and the kinetic energy, and for potential energy we have half m omega square x square. So from here we get a total equation, a total energy equation for simple harmonic motion, that is half m omega square x naught square. If you simplify, and you will see that the x are getting cancelled out, so we are left out with x naught. So if you are told to find the total energy, all the energies that we have are the kinetic energy, and the other one is the potential energy. So oh, that part is not being shown, it was covered. So we get a total energy of this. So you can whether substitute simply and do the maths or the calculations, or simply use this, which is much easier. And in the next video we will look at something which where we see here that no energy is lost here, and there is no dissipation of force. But what if there is a dissipation of force, and the energy, what should I say? The motion is not periodical, and it's not returning to the same. It's not. The positions are changing, and the forces are getting dissipated. So that will be covered in the next video. And for today, we